Continuing in Unit 8, Reactions and Solution, we're going to take a look at molarity. What we hope to do is 1. Define molarity, 2. Differentiate between what's known as concentrated and dilute as it relates to solutions, and then to do some problems, use 2 of the following quantities to determine what the third is. So molarity, volume, and moles, and volume technically in liters. Right. So solutions can vary in the amount of substances that they contain. Concentrated solutions have relatively large amounts of solute. Dilute solutions have relatively small amounts of solute. Hopefully that seems familiar to you. But what happens to the concentration of an aqueous solution if the container is left open? Well, if you think about it, if you leave a cup of water on your counter, what happens over time? The water evaporates, and then sometimes you'll see like a white solid material left if you let it evaporate all the way down. And that's the salts or the ionic compounds that had been dissolved in the water. If we take a look at this simulation of molarity, give me a minute, let me size it to the window. Okay. If I start off with drink mix and I have half a liter, you can see that my molarity of the drink mix is about 2 molar. And we'll get to that in just a minute. Now molarity is just a term for concentration. You can see that here, right? If I let that drink mix sit there and my water starts evaporating, say by half, what do you notice has happened to my concentration? Solutes typically do not evaporate, okay, at least not before the solvent. So the solvent leaves and you have particles of solute that remain behind. So it ends up getting more concentrated. Okay, so really the amount of solute stays in your sample of solution. What you can change is the solvent, the volume of solvent, either by evaporating it off to make it more concentrated or by diluting it to make it less concentrated. Okay, so, and we'll get back to that dilution and that concept. That's a very important concept, but we'll get back to that. So let's look at how we're going to use molarity. The moles of a solute in 1 liter of solution. We represent molarity by capital M. Capital M means the same thing as moles of solute per liters of solution. Okay, it can also be expressed in moles per deciliter. Okay. Deciliter, there are 10 deciliters in 1 liter. 1 deciliter is 100 milliliters. Okay, you need to know these relationships, that there are 10 deciliters in 1 liter and that there's 1 deciliter in 100 milliliters. Okay, so let's get to work on problems. Of course, we're going to use factor label. It asks, what is the molarity in moles per liter, which is actually redundant, of a solution in which you have 10 grams of silver nitrate dissolved in 500 milliliters of solution? Well, in solving the problem, keep in mind molarity is moles over liter. Moles of solute over liters of solution. Well, 10.0 grams silver nitrate. If you remember from past units, I can go from grams to moles using a molar mass. And I have 500 milliliters. So grams of silver nitrate in 1 mole of silver nitrate The molar mass of silver nitrate, 169.88. Grams of silver nitrate go away. I'm left with the moles. Now I have to get milliliters to liters. There's 1,000 milliliters in 1 liter. Milliliters cancel, and that will leave me with moles silver nitrate, which is the solute, over liters of solution. If I calculate the moles, the molarity, right? 0.152 moles of silver nitrate over liters of solution, or 0.152 molar silver nitrate solution. Okay, and that's how we would write it. Let's look at another example. I'm asked for the molarity of the chloride ions in a solution containing 14.5 grams of magnesium chloride dissolved in 250 milliliters of solution. Okay, so my givens, if I just underline them in the problem, 14.5 grams of magnesium chloride, 250 milliliters of solution. What am I looking for? I'm looking for the molarity of chloride ions. All right, so we're going to start off similar to how we did before. 14.5 grams of magnesium chloride, because I know I can get from grams to moles, over 250 milliliters of solution. All right, I want to get from grams magnesium chloride to 1 mole magnesium chloride. If I find the molar mass of magnesium chloride, 95.21. And then I have to get from 250 milliliters of solution, milliliters to liters. In 1,000 milliliters, I have 1 liter. So then I have moles of magnesium chloride per liter. That doesn't give me chloride ions. Well, if I look at magnesium chloride, solid, and I put it into water, it's going to form aqueous magnesium chloride. So how does that really exist in the solution? Well, it exists as magnesium ions and 2 chloride ions. So using this relationship, I can then relate 1 mole of magnesium chloride has 2 moles of chloride ions. Those cancels. The units I'm left with are going to be moles chloride ions per liter of solution. If I do that math, I end up with 1.22 moles. Looking at this number, though, I need 2 significant figures, so 1.2 molar chloride ions is my answer. Okay. And then another problem. How many grams of sodium hydroxide are needed to make 1.25 liters of a 0.400 molar solution? Well, here's given, here's a given, and I'm looking for grams. I think it's helpful to always rewrite this as moles of solute over liters of solution. Now if you look at that, if I multiply moles of sodium hydroxide over 1 liter times liters, I get liters to cancel. I'd be left with just moles. Can I go from moles of sodium hydroxide to grams of sodium hydroxide? I can. Okay, so let's start with 125 liters of the solution times 0.400 moles sodium hydroxide in 1 liter times in 1 mole of sodium hydroxide. How many grams of sodium hydroxide do I have? Well, that's just the molar mass. If I calculate that, I get 40.00. Moles cancel, liters cancel. I'm left with grams sodium hydroxide. And if I do that math, I end up with 20.0. See, 3 significant figures here, 3 significant figures there, so I should leave it 20.0 grams. And that's really using molarity, mass, moles, liters, any of those quantities to find any other quantity.